So this is the last learning unit for food chemistry, which is integrated approach to food chemistry, specifically packaging. Okay, so we're going to look at the effect of packaging materials on the flavor quality of food. Now, these are the learning objectives that you should be able to accomplish. The first one is to list the different type of packaging used for different food products. Secondly, to explain migration of compounds from packaging into food, and also absorption of flavor compound of food by the packaging materials. And then the next learning objective is to define BPA and its disadvantages. Now, packaging is a very critical component of food because it protects the food. And another way is to extend the shelf life of the food. Okay, so there are widespread and continuous use of plastic due to the development of various barrier products. Okay, means between the food itself and the environment. So one of the important or the issue is migration. Okay, migration of compound from the packaging into the food, and also the absorption of flavor compound of the food component by the packaging materials, which can alter the flavor profiles of the food. Okay, this figure here shows what will happen between the environment and the food stuff through the packaging material. Okay, so you can see this part here is the packaging, okay, which is made of the polymer film, of course. Okay, so permeation, okay, can occur between the environment and the foodstuff. Okay, so it's either way, from the environment to the foodstuff or the foodstuff to the environment. So that is permeation. So what are the migrating substances through permeation are oxygen, water vapor, carbon dioxide, and also other gases. Now, what are the consequences of these migrating substances are oxidation, okay, because of the oxygen, microbial growth because of the water vapor, okay, mold growth also because of the water vapor, off flavor because of the gases, okay, and also due to the microbial growth, okay, as well as oxidation. Next is dehydration and also decarbonation. Okay, so these are the consequences of permeation. Okay, we can say these are all the disadvantages. Okay, next is migration. Now, migration can occur from the polymer film or the packaging material to the foodstuff. Means, what are the migrating substances? Of course, from the polymer film itself, which are either monomer or the additive used on the packaging material. And these could lead to off flavor and also safety problems. Okay, safety means the ink used on the polymer film, for example, okay, migrated to the foodstuff and you eat. Okay, so that leads to the health issue. Okay, so safety problem there. Now the third one is absorption, okay, of the flavor component from the food to the packaging material. So what are the substances that undergo this absorption? Okay, the first one is aroma compounds from the food, the fat component of the food, the organic acid from the food, as well as pigments from the food. And this would lead to the loss of aroma intensity, development of unbalanced flavor profile, okay, And then we will look into detail of this in example in later slides. And also damage to the packaging materials. Okay, this one is very simple. Let's say you buy something that is wet, and then the packaging material is made of let's say paper, okay, polymer. So means it become wet as well because absorb moisture from the foodstuff and eventually torn apart. Okay, so that is example of damage done to the packaging material due to the absorption. Now, what are the packaging components? Okay, so the major component of a packaging material is polymers. Okay, one of it is plasticizers, for example, polyethylene glycol, and the use of plasticizers are to reduce brittleness and also to improve flexibility of the packaging material. The second type of polymer is catalyst. So catalyst is used in the production of polyethylene type of material, for example, antimony. The third one is antioxidant. So packaging material must have antioxidant property as well. Example of antioxidant use is tocopherol. The fourth one is blocking agent, and this blocking agent is used to prevent interaction between metal food container and food, and this is specifically for food packaging that is made of metal. The fifth polymer used is anti-slipping agent. For example, sodium bicarbonate, normally used to absorb oil and grease of the packaging material itself. Last one is ink, and ink of course is used to print the information of the food product. Okay, for example, the ingredients, the manufacturer, the name of the food, the weight of the food, okay, and many more. Okay, and it can be made of keto ester or any food dye. The second type of packaging component is solvent. So of course solvent is needed to make the packaging material. Now we will look at two different case study of what happened between packaging material and also flavor quality of food product. Okay, so the first one is migration of polystyrene cup residual compounds to oatmeal and grits. The second one is absorption of the orange juice flavor compound by the packaging materials. Now, the first one is polystyrene cups for oats and grits. And I'm sure you know what is polystyrene cups. Okay, you can still see it, especially in supermarket. Okay, food vendors for placing food so that it will retain the heat of the food. For example, when you buy corn in cups, okay, so they still use polystyrene cups. So what is polystyrene? Okay, so it's actually made of polymerization of styrene. Okay, so styrene undergo polymerization, you get polystyrene. So this is a chromatogram of a polystyrene cup. Okay, so there are 7 peaks here. Okay, peak 1, 2, 3, 4, 5, 6, and 7. Okay, so major peaks are peak 6, peak 2, and also peak 1. And what each of these peaks represent? Peak 1 represent N-butane, peak 2 represent ethylbenzene, peak 3 represent isopropyl benzene, peak 4 represent propyl benzene. And this table shows the content in ppm and also the threshold of each of these peak and the order of each of these peak. Okay, we continue with peak 6, represent ethyl toluene, peak 5, ethyl toluene, peak 6, styrene, and peak 7, methyl styrene. Now, these two chromatogram shows the chemical compound in the oats and also grits after it is placed inside the polystyrene cups. And we can see both oats and grits, okay, pick 1, 2, and 6. 1, 2, and 6, okay, are present, okay. So means the major compound of the polystyrene cups, okay, the one in high concentration just now, okay. So we can prove here this polystyrene compound migrated to the food component, and that is the reason why you see less usage of polystyrene material for food packaging. Okay, so you see a new type of packaging nowadays for food, okay, especially to pack hot food. For example, when you tapao from any restaurant, okay, you take away food, okay, they use different type of material now, and that material is made of polypropylene. Okay, number 5. Okay, so we look at the percentage of the residual compound migrated from the polystyrene cups to the oats and grits, and the major one are ethyl benzene and also styrene. Okay, so 13% in oat, 1.4% in grit for ethylbenzene, and for styrene 18% in oat and 2% in grits. Now, if we go back to the previous slides, okay, the threshold for styrene and ethylbenzene is only 0.73 ppm for styrene and 1.4 ppm for ethylbenzene respectively. Okay, but what is found in the food component is rather high. Okay, 25 ppm in oats and 2.7 ppm in grits for ethylbenzene. Okay, the threshold is only 1.4. Okay, for styrene, 13 ppm in oats and 1.4 ppm in grits, or also more than the threshold, which is only 0.73 ppm. Now we look at the second case study, which is absorption of orange juice flavor compounds by the packaging materials. Now, how is absorption calculated? We use this formula here, where the percentage of absorption is equivalent to the difference in terms of the concentration of flavor compound in control and in food sample. And then we times by 100, we divide with the concentration of flavor compound in control. Before that, let us look at different type of packaging material. Okay. The first one is low density polyethylene, LDPE. Okay. This is normally used to for squeezable bottle materials. Okay. The second one is polyethylene terephthalate, PET. Okay. This is normally used for soft drink bottle, okay, material. The third one is polyvinylidene chloride, PVDC. In the past, they normally use this as material for containers. Okay, containers. Okay, and normally labeled as number 7. Okay. The last one is ethyl vinyl alcohol copolymers, EVOH. We'll look in more detail of what are the application of each of these packaging material in the later slides. Now these are the chemical structure of each of the packaging material. Okay, LDPE, PET, PVDC, and EVOH. Okay, so if you look underneath or behind food packaging materials, you will see these numbers here in triangle. Okay, numbers, and each of these represent the material of the packaging, food packaging. Okay, so number one is referring to PETE, polyethylene terephthalate material. Number two referring to HDPE, high density polyethylene. Okay. 3, 4, 5, 6, and 7, so on. Okay. So this we'll look at the detail in the next slide. Okay. So if you look in this table here, it shows the different type of type and also manufacturer of each of these different polymer here. Okay, and these are the manufacturer, and these are the characteristic of each polymer. Okay, so the first three is non-polar. Okay, the rest is polar material. Okay, the value of its uh, glass temperature, okay, crystalline temperature, crystallinity, thickness, as well as its density. So this table here shows the different material. Okay, number 2, 3, 4, 5, 6, and 7 just now, and what are the material? Okay, and the application of each of these packaging material. Okay. So number one, I mentioned in the earlier slide, okay, used for soft drink, okay, plastic soft drink, okay. Number two, normally used for juice containers, liquid detergent bottle, okay, ice cream containers, bottle caps, okay. Number three is PVC, okay, normally for bottle with handle. Number four, low density polyethylene used for shopping bags. Okay, bread bag for frozen food bags. Okay, number five, of all of this number here, number five is the most durable. Okay, and it's made of polypropylene and used as food containers. So most of food containers now are made of polypropylene. Even your tapa packaging, okay, the recent type of tapa packaging, they use number five, okay, which can withstand high temperature. Okay, even can be used, especially and can undergo sterilization. Okay, for example, baby bottle. Okay, baby bottle. Number five. Number six is polystyrene. Okay. Number seven is other type of material. Okay. So number two, number four, and number five are highly lipophilic. So means it is hydrophobic. Okay. So means this type of packaging is inconvenient to pack food having non-polar characteristic, for example, food containing fat and oil. So if you have butter or margarine, you cannot use packaging number 2, number 4, and number 5. You have to use number 1. Okay. Okay. Other than number 2, 4, and 5. Okay. So number 1 is made of polyester, which are more polar. Okay, so means less affinity to be absorbed to absorb non-polar substance. Okay, so we use number one to pack uh, margarine or butter. Okay, so then there'll be no absorption of non-polar substance of the food component by the packaging material. Similarly, if you have food that is hydrophilic, so hydrophilic, we cannot use number one packaging. Okay, you use number 2, 4, and 5 type of packaging. Okay, so this is figure showing dynamic headspace analyzer gas chromatography. I don't have to go into detail of this. You have covered this under different subject. Okay. Now this figure here shows the GC. Okay, back to the second case study just now. Okay, so this figure here shows the chromatogram of orange juice flavor compounds. Okay, so the major compounds are alpha-pinene, ethyl butyrate, D-limonene, and octanol. Okay, these four are the major compounds uh, for orange juice. Okay, major flavor compound. Okay, this is the chemical structure of each compound, the D-limonene, alpha-pinene, octanol, and also ethyl butyrate. Now, this graph here shows uh, the absorption of D-limonene by different packaging material. Okay, so we have 4 different packaging material here. LDPE, low density polyethylene, we have polyethylene terephthalate, we have EVOH, we have PVDC. Okay. Okay, so the percentage of D-limonene absorption, okay, versus time in days increase, okay, increase drastically and then slowly, but still in increasing pattern except EVOH. But of all these 4 type of packaging, LDPE absorb the most. Okay, absorb the most of D-limonene. So if we use this type of packaging, okay, for orange juice means the flavor will change. The flavor of the orange juice will change because it has been absorbed by the LDPE packaging material. So the most suitable packaging material here, we can say PVDC. Okay, for the orange juice. Okay, so that is D-limonene. Now let us look at alpha-pinene. It also shows the same pattern. Okay, for the 4 type of packaging. Okay, again, LDPE absorb the most. Okay, absorb the most as the time goes by. Okay, so it will change the taste of the orange juice. Okay, if we use LDPE packaging material. So what can we conclude here? Okay, so the affinity of flavor compounds to the packaging material is depending on the polarity of the packaging material. So greater substitution rate is found if the flavor compound have the similar chemical structure or similar polarity as the functional group of packaging material. Remember, polar likes polar, non-polar likes non-polar. Okay, so the LDPE material will absorb more limonene and also alpha-pinene because these terpene compounds are non-polar compound. Okay, and their non-polar nature enables them to possess strong affinity for the non-polar LDPE material. Okay, so we cannot use LDPE to pack orange juice. Okay, so we can conclude that. Okay, due to this reason here. Okay, non-polar compound and non-polar material. Okay, so therefore we should use polar material instead. Okay. Okay, so this is the summary of the absorption. Okay. Okay, next we look at flavor compound and solvent interaction, especially during storage period. One of the example is commercial cherry flavor stored together with solvent like propylene glycol. Now, during the storage period, okay, interaction will happen, and this will lead to the formation of acetal. And this acetal formation is the compound that is responsible for the reduced in flavor, or in reduced in term of the cherry flavor. Okay, so therefore the intensity of the cherry flavor will be reduced in the food product, okay, due to the interaction between this cherry flavor and also solvent for propylene glycol. So this chromatogram shows the commercial cherry flavor, and also the mass spec of the propylene glycol acetal of benzaldehyde, and also toluoldehyde, means the acetal formation, okay, due to the interaction between the cherry flavor and also uh, solvent propylene glycol. Okay, this shows the interaction of the um, compound, the cherry flavor compound with propylene glycol, and leads to the formation of acetal, which are um, propylene glycol toluoldehyde and also benzaldehyde acetal. Okay, next we look at another case, okay, of migration from packaging materials to the food component. Okay, so mineral water sold in PVC bottle will contain a measurable amount of vinyl chloride monomer. Okay, and this vinyl chloride is a known carcinogen. So the Codex Alimentarius Committee on Food Additive and Contaminant has set a guideline of 1 ppm for vinyl chloride monomer in PVC packaging. Okay, and 0.01 ppm of the monomer in food. Okay, due to the reason that this will migrate from the materials to the food component. Okay, so these are the activity that we will do in our tutorial class. Okay, so you can start looking up on this information. Okay, the last part of this LU is BPA, or bisphenol A. So what is bisphenol A? Bisphenol A is a chemical commonly used in the manufacture of polycarbonate plastics like baby bottles, reusable water bottles, plastic baby toys, and also microwavable food containers. Now, what are the issue of this BPA? So scientists have discovered that this BPA may lead to, or even at low dose of BPA exposure, can cause cancer, impaired immune system function, obesity, hyperactivity, diabetes, and many more. So that's why I think you have heard of this issue many years ago, okay, many years back. So nowadays, especially if you look at baby bottle, it is labeled as BPA free. Okay, so they are no longer uh, made of BPA component in the baby bottles, okay, due to this issue. Okay, so BPA material in the plastic may leach out. Okay, leach out, especially when it is heated. Okay, like baby bottle. After usage, mommy tend to wash and also um, heat, heat the bottle. Okay, for sterilization purpose. Okay, and this will cause migration of the BPA component into the food or into the milk. Okay. Uh, or whatever that come into contact with that plastic and then consumed by the baby or the kids, toddlers and so on. Okay, so the safe BPA level is 50 microgram per kilogram per day, as stated by United States Food Drug Administration FDA and also US Environmental Protection Agency EPA. So in 2008, okay, um, Davis et al. And also Gibson in 2007 and also Polizu et al. In 2008 has done BPA analysis in all baby bottle, and all of these baby bottles showed significant level of leaching in the range of 5 to 8 nanogram per mil when heated only up to 80 degrees Celsius. Okay, normally when mommy sterile bottle, they use hot boiling water, which is of course more than 80 degrees Celsius. And that is why this BPA is banned as one of the material for baby bottle. Okay, so these are the different manufacturer or brand of baby bottle. Okay, I'm sure you are very familiar with Avon. Okay, besides Avon, they have conducted uh, for Gerber, Playtex, Evenflo, Dr. Brown's, and Disney. Okay, so Davis have done all. Okay, Gibson has done 5, and then Polizu et al. Done 3, and all of this detected BPA in the baby bottle. So that's why it is banned now. Okay, as component for baby bottle. So that concludes our last learning unit.